Clear the area, watch the support.
Run! Get out of here! The water's rising! Run! Hurry up!
We're cut off. Is anyone there?
It's 2:30 in the morning, October 1988. Deep under the Tsugaru Strait in Japan, a wall of water slams into a crew of tunnel workers with zero warning. No alarm, no radio call, just black water rising past their waists in total darkness. They are running blind through a passage that took 20 years to dig, a passage that has already swallowed 34 lives before this night even began. Somewhere above them, the sea itself is trying to take the tunnel back. This is not a disaster movie. This actually happened. And by the time you finish this video, you will never look at a tunnel the same way again. Because what looks like a simple hole in a mountain is actually one of the most violent, unpredictable battles in all of human engineering. Today we're going deep inside the longest tunnels on Earth. We'll find out why engineers who've spent their entire careers underground all say the exact same haunting line. The mountain always has the final word. Stick around, because the story of how humans punch holes through solid rock, under oceans, under the Alps, under cities, is stranger and far more dangerous than almost anyone realizes. Here's a question you've probably never thought to ask. Why is digging a tunnel considered more dangerous than building the tallest skyscraper on the planet? The answer will completely change how you see construction. When engineers build a bridge, a tower, or a dam, they can see everything before the first shovel hits the ground. They survey the land. They test the soil. They model every possible stress. Nothing is a mystery before construction even starts. Tunneling flips that entire process upside down. Engineers begin with nothing but a geological map stitched together from surface scans, a handful of bore samples, and seismic echoes bounced off rock nobody has ever touched. Then they send a machine straight into that guess and discover, almost immediately, that the Earth has other plans. Solid granite can vanish without warning into a pocket of soft clay that swallows a boring machine in minutes. A fault line that never showed up on any survey can cut diagonally across the planned route, holding back water under pressure that could kill an entire crew in seconds. Every single meter forward is a step into a place no human being, no sensor, no map has ever verified. The only way to know what's really down there is to go and find out, and sometimes that discovery arrives all at once, violently. What if I told you the tool used to dig these tunnels isn't really a drill at all? It's closer to a self-contained underground factory, one that eats rock on one end and builds a finished tunnel on the other. That's the tunnel boring machine, or TBM, and once you understand what's actually happening inside one, you'll never think of drilling the same way again. Forget any image of a simple spinning bit. A large TBM can measure 10 to 15 meters across, wider than a 3-lane highway, and stretch back more than 100 meters behind its cutting head like an armored train fused to the front of a factory. At the very front sits the cutter head, a massive rotating disc lined with hardened steel cutting wheels that grind directly into the rock face in a slow, relentless circular motion. As that head turns, hydraulic rams shove the entire machine forward with a force measured in thousands of tons, enough raw pressure to crush a car without slowing down. The crushed rock, known in the industry as muck, gets scooped up by buckets built into the cutter head itself and dumped onto a conveyor belt that runs the entire length of the machine, feeding it out to waiting rail cars. And here's the part that sounds almost like science fiction. As the machine crawls forward, it simultaneously builds the tunnel behind itself, using robotic arms to lift massive precast concrete segments into place and lock them into permanent rings. It bores. It hauls away the waste. It finishes the walls. All at once, in a single continuous motion, advancing anywhere from 5 to 30 meters a day, depending on what the rock decides to throw at it. Now picture standing inside one of these machines while it's running. The noise doesn't just hit your ears. It goes straight through your entire body. The whole structure shakes constantly. Temperatures inside can climb past 40 degrees Celsius, hot enough to soak a worker's clothes in sweat within minutes. And just centimeters away from where you're standing, on the other side of a steel shell, is raw, unlined rock under pressure so extreme that the machine itself is the only thing holding it back. So, if the machine is this powerful, why do tunnels still take decades to finish and still kill people? Because the TBM is only as good as the ground it's fighting, and the ground never fully cooperates. There are 3 enemies down there, and each one has humbled some of the greatest engineering teams on the planet. You'd think solid, Hard rock would be the easy option. It isn't. Extremely hard rock grinds down the TBM steel cutting discs so fast that crews have to replace them every few hundred meters, and that means sending human beings directly into the pressurized zone right in front of the spinning cutter head, widely considered one of the single most dangerous jobs in all of tunneling. The Gotthard Base Tunnel in Switzerland, the longest railway tunnel in the world at 57 kilometers, chewed through more than 3,000 disc cutters during construction. Each replacement meant workers stepping into conditions that pushed the human body to its absolute limit. In loose or mixed soil, the TBM has to constantly balance pressure against the tunnel face using compressed air or a pressurized slurry mix, almost like holding a giant water balloon in perfect equilibrium. Get that balance wrong by even a small margin, and the tunnel face can blow out explosively, sucking debris violently into the machine, or collapse inward and bury the TBM completely. This isn't a rare theoretical risk. Multiple massive boring machines around the world have been permanently abandoned underground after getting swallowed by the very ground they were digging through, sealed forever inside the tunnels they never finished. Underground water doesn't politely wait for a survey to find it. It hunts down every crack, every joint, every hidden weakness in the rock, and when it finds one, it arrives carrying the full crushing pressure of everything sitting above it. At the depth of the Seikan Tunnel, water pressure exceeded 24 atmospheres. At that pressure, a breach in the rock doesn't trickle. It doesn't leak. It erupts. The Seikan Tunnel runs 53.8 kilometers beneath the Tsugaru Strait, connecting the Japanese islands of Honshu and Hokkaido, plunging as deep as 240 meters below sea level at its lowest point. From day one, engineers knew water would be the single greatest threat to the entire project, so they developed a technique called pre-excavation grouting, injecting pressurized cement and chemical compounds directly into the rock ahead of the machine to seal off water-bearing cracks before the boring face ever reached them. But there was a problem no amount of preparation could fully solve. The seabed beneath the Tsugaru Strait had been shaped by millions of years of seismic violence, riddled with faults and fractures too numerous and too irregular for any grouting program to catch every single one. In October of 1988, one of those hidden faults finally broke through. An estimated 70 tons of water per minute poured into the tunnel before engineers managed to seal the breach using a desperate combination of emergency grouting and nonstop pumping. It took weeks just to drain the flooded section. And then, incredibly, construction simply resumed. The tunnel that had already claimed 34 lives, that had just tried to drown its own workers, was finally completed later that same year, closing out a construction saga that had begun all the way back in 1964. Here's something almost nobody thinks about when they picture a tunnel under construction. The air itself is trying to kill everyone inside. Deep underground, at the depths and distances involved in major tunnel projects, natural airflow is essentially zero. Left unventilated, the air inside an active tunnel becomes a toxic cocktail of diesel exhaust from heavy machinery, fine silica dust kicked up by rock excavation, and carbon monoxide released during blasting operations. Without constant, forced ventilation, a worker could lose consciousness in a matter of minutes. To fight this invisible enemy, major tunnel projects build an entire secondary system, a parallel ventilation network, often running through its own smaller pilot tunnel alongside the main bore. Fresh air gets forced in under pressure through one set of ducts while contaminated air is violently sucked out through another. In the Gotthard Base Tunnel, this ventilation system had to deliver breathable air across the full 57-kilometer length of the mountain to multiple crews boring simultaneously from both ends and from two separate access shafts in between. Designing that single system alone consumed several years of dedicated engineering work, and the job doesn't even end when construction finishes. Once a tunnel opens, that same ventilation infrastructure has to manage exhaust from thousands of vehicles, or the violent air displacement caused by high-speed trains, every single day for decades to come. What happens when you take every single one of these threats, hard rock, soft ground, water, heat, and toxic air, and stack them into one 17-year project underneath the Alps? You get the Gotthard Base Tunnel, and its story reveals just how enormous the gap can be between what a map predicts and what the Earth actually contains. Construction began in 1999 and didn't finish until 2016. Along the way, crews ran straight into nearly every geological nightmare that exists. They hit squeezing ground, zones where rock under extreme stress slowly oozes into the tunnel opening like unbelievably slow-moving toothpaste, forcing engineers to redesign the tunnel lining mid-construction just to handle deformation nobody had planned for. They tunneled through a notorious rock formation called Tavature Intermediate Gneiss, so wildly unpredictable under stress that it dropped the machine's advance rate to less than a meter per day for extended stretches compared to a design target of 12 meters a day. They pushed through zones where geothermal heat inside the mountain reached 46 degrees Celsius, so intense that engineers had to install cooling systems not just to protect the machinery, but to protect the workers themselves, whose core body temperatures were at real risk of climbing to dangerous levels from the heat of the rock alone. 9 workers lost their lives during construction. In total, more than 2,400 kilometers of tunnel were carved out across the entire Gotthard system. Once you count every parallel service tunnel, cross passage, and emergency station built alongside the main bore. And at its deepest point, the finished tunnel sits under rock loads equal to 2,450 meters of solid mountain pressing down from above, nearly the height of 8 Empire State Buildings stacked on top of the tunnel roof. Every time a train speeds through one of these tunnels, it's riding through a structure engineered with a level of precision most people would never expect from something that looks, from the outside, like a plain curved slab of concrete. In most modern bored tunnels, the permanent walls are built from precast concrete segments, assembled ring by ring as the TBM advances. Each of these segments weighs somewhere between 5 and 8 tons, yet they're manufactured to tolerances of a single millimeter or less, because they need to lock together into a perfectly sealed circle capable of resisting ground pressure, water pressure, and constant traffic or train loads for a design life of roughly 100 years. In squeezing ground, these linings have to be engineered to flex slightly as the rock shifts, absorbing the movement instead of cracking under it. In water-bearing ground, every single joint between segments has to be sealed with gaskets rated to stay watertight for the tunnel's entire century-long lifespan. What looks like a simple curved wall is actually hiding reinforcement patterns, concrete mix formulas, and manufacturing tolerances that rival the precision demanded by aerospace engineering. Behind every impressive statistic about tunnel length and boring speed is a number that rarely makes it into the highlight reel, and it's the number that matters most. Tunneling remains one of the most dangerous construction disciplines anywhere on the planet. Confined spaces, heavy machinery, explosive blasting, geology that can turn hostile without warning, and the constant threat of flooding or collapse combine to create an environment where there is almost no margin for error. The Gotthard Base Tunnel's toll of 9 deaths across 17 years was actually considered low by historical standards for a project of that scale. The Mont Blanc Tunnel killed 60 workers during construction in the 1960s. The Seikan Tunnel killed 34. The Channel Tunnel, dug beneath the English Channel between England and France and completed in 1994, killed 10 workers before it ever carried its first passenger. These aren't just statistics buried in an engineering report. They're real people whose names never made a headline, whose families carried the weight of decisions made in conditions no map could predict and no model could fully anticipate. So, after all these disasters, all these deaths, all these near-catastrophic floods, has anything actually changed? The answer is yes, and it's some of the most fascinating tech in modern construction. Real-time geological sensing now lets TBM operators analyze the material coming off the cutter head as it happens, adjusting the machine's behavior before a small problem becomes a full-blown crisis. Ground-penetrating radar mounted directly on the cutting head can peer ahead of the machine, spotting hidden water-bearing faults and voids before the boring face ever reaches them. Automated monitoring networks now track ground movement, water pressure, and tunnel deformation continuously across thousands of measurement points, feeding engineers data that can flag a developing problem day or even weeks before it turns into an emergency. None of this technology has erased the fundamental unpredictability of digging through solid earth. Nothing ever will. But it has shifted the entire discipline, just slightly, from reacting to disaster after the fact to anticipating it before the mountain gets the chance to strike first. So the next time you're driving or riding a train through a long tunnel and you catch that first glimpse of light at the far end, take 1 second to really think about what you're passing through. It isn't just a hole. It's the physical scar left behind by a decades-long negotiation between human ambition and an underground world that fought back at every single step. Somewhere in that concrete lining is the answer to a geological surprise nobody saw coming. Somewhere in the ventilation ducts running beside you is the solution to an air quality crisis that took years to crack. And somewhere in an engineering archive, there's an original geological map that, compared to what the machines actually found underground, reads almost like a work of fiction. The mountain always has the final word. The engineers just spent decades learning how to get enough words in first. If you want more deep dives into the hidden engineering holding our world together, make sure you subscribe, because what's coming next is even bigger.